Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. Hey everyone, hope you all had a wonderful holiday. Over the next few weeks, we'll be running back the clock with our second annual AI Rewind series. Joined by a few friends of the show, we'll be reviewing the papers, tools, use cases, and other developments that made a splash in 2019 in key fields like machine learning, deep learning, NLP, computer vision, reinforcement learning, and ethical AI. Be sure to follow along with the series at twimlai.com/rewind19. As always, we'd love to hear your thoughts on this series, including anything we might have missed. Send me your feedback or favorite papers via Twitter, where I'm at Sam Charrington, or via a comment on the show notes page you can find at twimlai.com. Happy New Year. Let's get into the show. All right, everyone, we are here for AI Rewind, our second annual walk through the top trends and developments in machine learning and AI. And this time, I am with Amir Zamir. Amir is an assistant professor of computer science at the Swiss Federal Institute of Technology, or EPFL. In fact, Amir, at this current moment, for another 3 days, is a postdoc affiliated with Stanford and UC Berkeley, where he was when we first spoke with him back in July of 2018. Amir, welcome back to the TWIML AI podcast.
Thanks. Great to be here.
Yeah, I'm really excited to dig into this conversation about what's new, your take on 2019 from a computer vision perspective. And so to kind of get us started with that, why don't we just take broad brushstrokes? What's your take on 2019?
Thanks for having me. It was another exciting year, in my opinion, for fields within AI and including computer vision. Conflict conferences are expanding, so there's more talent coming in, more energy. I think CVPR 2018 was 6,000 roughly, the number of attendees, in 2019 was about 10,000. So we'll see, and that was 6 months ago roughly. So we'll see how it's going to be in 2020, but that expansion in size.
How does that growth rate compare to NeurIPS, which is the one that gets a lot of headlines?
Right. NeurIPS was, I came back from NeurIPS like roughly 2 weeks ago. I believe it was 13,000. But again, they are like 6 months apart. So, we will see how CVPR will be. But I think roughly the same size, maybe NeurIPS somewhat bigger, because it generally includes many different areas, not just vision, not just NLP and so on. Many vision people are there, myself included. But they are a huge conference. It's big enough that you won't see your friends anymore.
And are the paper submissions at CVPR growing as quickly as NeurIPS?
Yes. Yeah. I don't know the exact number this year, though I'm an area chair, so I should know this number. But all I know, what I'm sure about, is that there was a really sharp expansion, and to some extent that presents a problem for us academics, because we have to find reviewers for this load of like papers and so on. But that's fine. That's a good problem to have. The overall outcome is positive, albeit with some variances. The growth was in a way disproportional, because now for the past like 4 or 5 years, there was a huge interest. And so we have a lot more like young talent in the field. For the same reason, they're young and new. So we don't have as many seasoned reviewers to evaluate the papers for us. So to some extent, the review quality has a little bit of variance in it compared to a few years ago. But again, like I said, that's a good problem to have, because the field is just generating more results. So a little bit of variance is, in my opinion, acceptable.
So the field is growing dramatically, as are other areas in ML and AI. What else is happening in vision?
Right. In terms more technically, I think we see a few trends that they're not too exclusive to 2019, but I think some of them are like maturing up in 2019. One meta trend that I see for sure is that we see a lot of mixes of areas, like vision plus something else, like vision plus graphics, I think a nominal example of that are all these like image synthesis pipelines, either GAN based and whatnot. But the pipelines that essentially generate an image, that's in a way it's a graphics problem, because graphic is about like generating something good looking that you put on your screen, like rendering things. And vision was the inverse of the problem. You already have an image and you want to understand it. But these two areas got blended together. And I think the first time in Vision that I saw a reasonably working example was the paper Pix to Pix a few years ago. And
Mm-hmm.
after that, it became really popular, and CycleGAN and so on. Those other papers actually came primarily from the Vision community. And of course, the graphics community worked a lot on it too. So so mixes of areas, vision plus graphics. I guess we'll discuss it partially when we get into more details. Vision plus robotics is expanding. I think it's one of the areas to watch for sure. Vision plus like adversarial robustness literature. I think that's something that not many of us saw it coming, but in a way it actually makes sense. That how the algorithms that basically there was a line of research going forward on making machine learning systems more robust, and that there are several examples were like posing concerns to people. It turns out that if you have more robust algorithms for processing visual data, they are more useful toward just processing non-adversarial literature and non-adversarial content as well. Like if you have an image synthesis pipeline, it works better if it was robustified, even if you don't mess with the input anymore.
Right.
We can discuss in more detail as we go forward. But I think generally the trend of mixing different areas with vision is increasingly popular. And I think there's actually a healthy reason to this. I think it's a realization of the fact that vision is a service to some downstream goal. It's a very powerful skill, but we don't usually observe the world for the purpose of just absorbing, like just understanding what's going on. We usually have an intent in mind. Like we understand the world with, when I get up in the morning, when I open my eyes, I intend to get out of bed safely and navigate myself out of the bedroom. So the vision is a very practical skill. And so we cannot really make that independent, the research that we do on vision, of these downstream skills. So vision plus X is, to me, I see that as realization of that fact, especially in the context of robotics. The reason we mix vision and robotics together is that our robots need to have a complex understanding of the world acquired through the cameras. So whatever the vision pipeline outputs, it should be in a way curated to best support the downstream goal of a robot. I particularly don't care, for instance, if I have a robot in my home and it can detect all the objects and do all sort of like complex things. I don't really care how the vision pipeline works if the downstream goal of a robot, whatever it is, make the bed or do laundry or whatever that is, if that works just fine, the vision can be as simple as it wants to be. And so it is really an end-to-end intertwined pipeline. And I'm actually happy to see that these areas are mixing together, because we can now do a more meditated design in our research and do vision in a way that it's more useful toward the downstream goals. There are some caveats to this story. For instance, art. When I observe a painting, I'm watching it, I'm looking at it, but I'm appreciating it. I don't necessarily intend to do something with it. But generally speaking, vision is a very practical skill, and mix of areas, in my opinion, is a realization of that.
Is there also an implication that vision has reached a level of maturity, or meaning the core vision tasks have reached a level of maturity or performance that we can now even consider moving on to real world types of things and incorporating in these other areas? Like we've solved enough of core vision to, then mix it with these other fields?
Yes and no. I would I would be really hesitant to say that we have solved enough core vision problems, or we have solved them like fine. I actually think, let's say the simplest example, probably the longest running problem in vision is, let's say, object detection. We are not at a point that we can say that we can, with a high confidence, we can detect an object under varying lighting conditions in different contexts and so on and so forth. So, but at the same time, a huge amount of progress has been made. Whether there's a way to make them useful, I think the answer is yes. And that's why many people that are not vision experts are actually using vision pipelines. And we see APIs as well. So on Microsoft or Google, there are APIs where you can do somewhat niche problems, but they're sufficiently reliable, something like face detection. So the fact that we have APIs that non-experts can use at the command line level, that basically means, yes, a certain level of maturity has been reached. But that does not mean that we can solve the problems now that seemingly are simple, because we have huge problems in that, like specifically 3D, like 3D perception. We have a lot of sensors for it, and these sensors are expensive, such as LiDAR and so on and so forth. But understanding the 3D the content of an image in terms of 3D is far from like perfection. So there's a lot more work to do.
We've got the field growing in size. We've got this mix of areas being explored. Any other general trends that you're seeing in vision?
I think in general, we see less and less fixed pattern recognition problems. Like I said, object detection or segmentation and so on. That's going forward too, and that's going forward strong. We see progress, but the attention and energy from what I see is like shifting towards these like new horizons that are opening up right now. And I think there's like generally also interest in unsupervised or self-supervised learning has been growing, and it continued to grow. And I think there was some good progress in the past year, but that's not something that I anticipate being solved anywhere in the near future. So I think we'll continue to see that as a significant area of research.
And let's transition to some of the specific areas that you've identified to dig in deeper. When we asked you to identify, just a few papers that you thought represented the kind of progress that we've made in vision as a broad field in 2019, you found that particularly difficult to do. Can you talk a little bit about why and the areas that you've identified to discuss with us?
There are a number of areas that I think it's worth discussion. Like I said, like when you have a conference with 10,000 people, and that's just CVPR. We have ICCV and ECCV as well, at least as like top tier vision conferences. I mean, you can imagine that there's a lot of research going on, thousands of papers coming out. So it's hard to just pick out one or two or five papers because there's just more good work than those numbers and a handful of papers. But I think in terms of we can summarize the trends. One trend that I specifically see and I expect to grow is Vision-for-Robotics. So general interest in robotics is growing, especially in what usually people refer to as like robot learning these days, like reinforcement learning platforms, or generally mix of learning-based robotics with the classic robotics. And vision is part of this story. Like a robot is a large, like intertwined, like framework, and it involves like multiple aspects, like sensory hardware, perception, planning, control, and so on. And one common question is like, what makes vision, and like robotics then? These days, especially with the rise of like robot learning, where like one of the frequent claims is learning directly from raw pixels.
Right.
So one question is like, why we need like a specific vision algorithms at all if all we can do is like learning directly from pixels. So first, like I draw the line between vision and, let's say, control, uh, acknowledging that this sort of intertwined pipeline and clearly end to end. Sensory observation comes in, goes through vision, goes through planning, goes through control, goes through hardware, and the robot in the end does something. So it's an end-to-end pipeline, clearly. But to me, as a vision researcher, what makes a vision research is a robot has some sensory hardware, like a camera, and these sensors observe something and have some output. The algorithm that just processes this output and extracts some useful abstractions out of those high dimensional sensory data, that's the perception problem. So if the processing pipeline, that black box, sits closer to the sensors, it's more about understanding the world because those sensors are sensing the world. So the type of priors that those black boxes use are about, like, let's say the world is 3D, or there's some dynamics in the world, there's like motion smoothness and so on. So perception uses these priors to tame these high dimensional signal, and then hands that over to the rest of the pipeline, let's say planning and so on. So the closer to the end we get, then comes the problem of control. Like having these abstractions and having planned something, you want to issue an action that the robotic hardware executes for you. So to me, vision researchers are in the beginning of this end-to-end pipeline. They are more concerned about the world. They use the priors about the world and turn that into processing pipelines. And robotic researchers get these more abstractions and are closer to the agent. They understand the hardware, the robot better, so they control the robot so that they execute something that in a way that after doing multiple of these iterations, the outcome is achieved. So like I said, this is immediately brings these multiple fields together, vision plus robotics, and it calls for us vision researchers to develop this vision box in a way that it can support the rest of the pipeline the best. It's not an open loop system. It's not like we receive a sensory observation like images and produce something, an object, for instance, object detection, and then we just say we don't care about what's going on after that. It is really important what comes after that. For instance, uncertainty estimation. It's really important for control theory people. So it makes sense that as vision researchers, we become aware of that and provide some form of uncertainty estimation that is tied with our detection and so on and so forth. So I think there are a number of clear developments in the field acknowledging this vision for robotics type of research.
You drew a distinction early on in this between, and I want to get this distinction. I don't think I'm going to get this distinction correct, so please correct me. But it was something along the lines of, vision versus learning from pixels.
Right. Well, vision is learning from pixels.
Right.
I see. So I understand. So yeah. So there's actually tabula rasa learning. It's a common word. It's not actually new. It's called I think it's Latin. It means like clean a slate. Mm-hmm. So a system that, let's say, a robot that does tabula rasa learning in terms of vision, what it does is that, okay, I have the sensory output, just raw pixels, and I'm gonna learn directly from raw pixels. Let's say, for instance, using a model-free reinforcement learning policy. And then you define your goal in terms of some reward function that like rewards you when you do something right and penalizes you when you don't do that right. And then you hope that by just direct interaction with the world, many data points, the system will learn how to do the job right. And that's generally what we see in reinforcement learning literature, especially like in model-free reinforcement learning. But there, the distinction is that learning directly from raw pixels, it basically means the state of the world are these like raw pixels. I'm by the way, I'm generalizing a lot here to get the general concept right.
Sure.
What vision is about when we are processing these raw pixels, instead of just using them raw, viewing them as like a 2D matrix that is coming from the camera, so that's what we know. Vision is about like having some priors about the world, and instead of using this signal raw, we use those priors to extract some abstractions that are easier to understand. They're more interpretable, they're more efficient, and so on. So an example, like I said, is the fact that the world is 3D. So when you look at an image, it's a projection, 2D projection of a 3D world onto a 2D plane. So it basically loses the 3D information. So if a robot is trying to make use of this 2D projection, it has to somehow recover that information. So either we hope that by these like millions and millions and millions of interaction, this robot actually understands 3D reconstruction to some extent, at least, to be able to solve the problem, because we know that some of these problems, especially in navigation, they need 3D perception. Like, you need to know how far the obstacle is to be able to avoid it. So there's no like escape from that problem, at least at the course level. So either the hope is that by not providing these priors directly and learning directly from pixels, the system, by many millions of interactions, it learns that. Or some people, like vision researchers, they use these priors about the world, they extract these abstractions out of the raw pixels, and that's what the rest of the system, for instance their enforcement learn policy, uses. So
So,
you can view basically vision as identifying these like facts of the world, the fact that the world is 3D, the
mhm.
fact that there's like motion and smoothness, turn them into a processing pipeline. So when the raw image comes in, it first goes through these abstractions, and then those abstractions are what the rest of the system, like the robotic system, sees. So they're more interpretable, they're easier to tame, and you don't have to like redo this process every time that you turn a robot on during the learning phase, because these
Mhm.
are just facts about the world that are generally true. It doesn't matter whether you're navigating or you're manipulating or you're finding an object or you're just going GPS coordinate. You need some understanding of about 3D from the world. So it makes sense to turn that into more like a standalone problem
Yeah.
where vision people solve, and then plug that into the bigger pipeline.
Now, when I talk to folks that are coming from the opposite direction or the other direction,
Mm-hmm.
the pixel based learning and reinforcement learning, one of the things that they say is hot this year is model based reinforcement learning, for example, where they're trying to learn a higher level model in the process of learning from the pixels to do some of the things that you're describing. And I
Mm-hmm.
guess the question that I'm asking is, does this mean that vision and the pixel based approaches are converging, or is it saying something else? So those models in the
Mm-hmm.
model based RL, are they the same kind of abstractions that you're describing
Right.
that are core to vision?
Right. I mean, model-based RL, or generally model-based everything, is it's too general to the point that it can include anything and everything. So, for instance, model-based, yeah, you can have a model based on the 3D of the world, and
Right,
that would
right.
become model-based something. So, um, this doesn't necessarily mean there is a completely orthogonal approach to solving this problem that is going to replace vision or anything. Generally, when you have a model, you're encoding some priors. Either you're learning these priors,
Mm-hmm.
or you're encoding them into the system. And like I said, vision is more or less about that too. We define some abstractions that we believe are generally true about the world, and we focus on solving those. Up until a few years ago, we were doing it completely independently of who uses the output, like a robot. But now, like I said, with these areas being mixed, we are developing them in a more end-to-end manner, with the awareness that we need to develop them in a way that they're best useful to the rest of the pipeline. But yeah, in the end, it's all the model, and there are like people call different things a model. There's like dynamics model, which is about like prediction of the outcome of a certain action, so that helps with like efficiency and so on. But for generally being able to solve this problem, you need to have a model, and we are all in the business of developing that.
Okay. So, what are some of the specific papers that kind of exemplify this trend for you?
Yeah, so for Vision-for-Robotics, like I said, the vision community primarily focused on the navigation. There are good reasons for that. Again, I think one of the most important things that are probably enlightening here is to look at the data, like where we get the data for being able to develop a vision model for an agent that is active in the world, like a robot that does navigation.
Mm-hmm.
So it's a big question. It's a very different from, say, an offline data set that sits in the hard drive of a computer, like an ImageNet. You take a picture once and that's it. You annotate it. You have no control over this pixel any longer. You cannot say, like, let me move a little bit in this image, like, let me look at the same object from left or right and so on. So this pixel is like pre-recorded and is offline basically. Now, by definition, active agent has some degree of freedom. So it can do something, it can move around, for instance, if it's a navigation agent. So there's a gap between like static and offline data sets and the type of data that developing vision for robotics involves. We basically need to have some online pipeline for generating data. And that's usually why people use simulators. Again, till a couple of years ago, the simulators were primarily based on synthetic data. These are synthetic data, meaning that a designer would sit down and model, let's say, an apartment for you by putting together some CAD models of chairs and tables and so on. And there would be a computer graphics pipeline that renders that into pixels for you. And we would use that as a source of data. And that would solve the problem of being active because, of course, you can just shift a little bit in this scene and re-render it. So it would give the possibility of a degree of freedom to the agent that is using the data. But the main problem was that the data was not then from the real world. So there would be no guarantee that this would generalize. And generally speaking, since computer graphics is not completely solved yet, so the type of pixels that we get as a result of this are not fully photorealistic. And even if they were fully photorealistic, the underlying semantics are coming from a designer, and the designers have biases too. So if you look at let's say some of these models that existed in such data sets like SunCG and so on, it's the moment you look at an image, it's immediately clear that they are coming from a simulator. They're not from the real world. And what gives it out is not just the fact that the pixels are not like photorealistic, is the fact that these models are usually too clean. No designer would sit down and design, say, a very messy bedroom and so on and so forth. So there was a photorealism gap, but there was a bigger actually semantic gap. So since a couple of years ago, what changed, and I think in my opinion was actually a big change in the community, was that data sets came out that they're based on scans of real world buildings. And then CVPR 16, we had one paper called Building Parser. It was, I believe, the first time that multiple large buildings were scanned using like commercial scanning pipelines fully in 3D. So you would have a mesh of one building. I remember at that time we had, I think, 6 buildings of a Stanford scan. So you could load the mesh in your computer and look at it, and it's the entire building is at your disposal. So that later became a underlying model for many simulators. And now the simulators, instead of using the designer to develop things or design things for you, now there's actually a real building that is serving as the underlying data. And so multiple data sets came out of that. One of them is called like Stanford 2D 3ds, Matterport 3D, and Facebook Replica, and so on. That was actually the last one in this time-wise. In Gibson in 2019, there was a 2018 in CVPR, we had the paper in Gibson that had brought that to really large scale. There was about 600 buildings that they were scanned. So a robot can virtually visit 600 buildings, interact with it in as far as navigation is involved, of course, and learn from it. And 600 is a lot. If you go to a new building every week and visit all corners of it, because these scanners like scan everything. If you go to a new building every week, it takes 10 years to get through 600 buildings. So there's a lot of visual data, certainly more than what like humans probably observe. By the end of age 2, that's where like vision is sufficiently developed. So that wasn't an excuse anymore, essentially lack of data.
Given the constraint that you mentioned on how long it takes to scan these buildings, was the data crowdsourced?
Yes, to some extent. We spoke with we had like cameraman. Some of them we would send them to actually scan buildings for us. Some of them would have scans already, so we would acquire it from them. But yeah, we didn't actually scan them. It was like people's that would scan them for different reasons. Then we would acquire them. And there's actually, since the scanning pipelines, 3D scanning pipelines are now sufficiently mature, there is actually a support chain for them, primarily coming from real estate market. most of the, I'm not actually sure if it's most of the houses, but a good percentage of the houses, if you want to sell them well, you have to scan them in 3D so you can put up a website for them, so the buyer can navigate in it before they actually come see it and so on. So that's actually a good resource of data for us, and that actually created a supply chain of cameramen that you can probably any city, at least in the United States and Canada, you can hire a cameraman that already has the camera and they can go scan, and then within a few hours they can send the model.
This habitat competition, this is a benchmark that Facebook is proposing for agents that are navigating spaces. Can we talk about what the kind of, how do they quantify performance in this environment?
Right. Yeah. It's built. Facebook has a team of software engineers and researchers that developed the Habitat platform. Like I said, to a large extent, it was developed on top of Gibson and a few other works that exist in the community, like I said in the past, like Minos and so on. So the way it works in general is that the tasks are specific, like point nav or point navigation. The agent is dropped in a new building, completely unseen, and it's provided at a random location in a new building, and it's provided with the coordinate to go to. So the agent could be randomly spawned in a bedroom, and the coordinate that it's provided as the goal location is somewhere in the living room. And all it sees is a stream of RGB or RGBD data. And it has to now plan its way around the obstacles and safely navigate itself to that particular location, which could be like tens of meters away. So it's a hard problem to solve, especially that this is a new building. It's not like you could spend time scan this building, something like a SLAM pipeline, and then run ASTAR and something like that to plan, like post plan a trajectory. It's just like imagine as a human when you go to your friend's house when they just bought a house, so you have never been there, and once you enter the living room and you want to use the bathroom, you can probably think about, okay, the bathroom would be probably, I need to be looking for some hallways or doors, and maybe with a little bit of search, you would find your way to the bathroom. But you would not be just randomly wandering around in this building for hours and hours till maybe by chance you would find the bathroom.
Right.
So these agents actually, the task is something similar to that. Completely unseen building, spawned in a random location and provided with a target coordinate. Just travel to it. So that was the first competition of Habitat in 2019. And there were actually a lot of entries. I don't know the exact number, but there were enough to actually make a good competition. There were 2 tracks, and they were not about the task, but they were about the type of data. So if the agent, all it sees is RGB, that would be akin to having just an RGB camera on a real robot. That would be RGB only track. And there was another track which was RGBD. That would be like having a 3D sensor to like connect. Now we are at a point that we have a challenge where like tens of teams enter, and there is a good amount of energy in the community that is spent in this area. So it's to me, it's actually a very healthy progress towards vision plus robotics in this context. And this, like I said, the robots are limited to navigation now. And the reason for it is that our data platforms right now can support only navigation, not manipulation. Technically speaking, it's hard to scan a building and now go make a change in it and be able to render it. These buildings are scanned statically. So we don't have a good like support pipeline yet as of now for capturing both dynamic content and interactive content. There's work going in this direction in the community too, but I think it's I would summarize them to be still in a scouting stage when they're infancy. So we'll see how that plays out in a few years. But navigation is something that it's a reasonably stable. We have good data platform for it, and we can look at the output. And to be honest, like I was personally impressed by the performance of the winning teams in both tracks. It's actually a hard problem to drop an agent in an unseen building and give it a goal that is like tens of meters away Navigating the path is hard because you need to identify a lot of things. You need to know, for instance, where the doorway is to get yourself out of the room. And the moment you're out of the room, you don't want to hit like the walls or many obstacles in the way. And then maybe the target is behind, let's say, a chair and so on. So there's a lot of like a fine-grained planning that goes into successfully doing that. But the success rates are actually higher than what I expected. So hopefully in the next year, we'll see this becoming more mature. And the task, of course, need to be more realistic. Point navigation is probably the simplest one. We need to be able to navigate towards like move towards semantic navigation. Let's say if you task an agent with finding a key, the key doesn't have a specific coordinate. It can be anywhere, but it's not in arbitrary locations too.
Are there any other kind of highlights in the Vision for Robotics field that you want to touch on before we move on?
No, well, I think this was Habitat was and Gibson and so on were actually a good representative of the progress. In terms of the discussion that we had earlier, is like if you can learn everything from raw pixels, what would be the need for like vision? There were actually multiple papers that came out in this area that they had focused the studies on why actually it is critical to have vision pipelines when you're trying to do robotic tasks. One of them was a paper that we did. We published in last year, I believe in December 2018 on Archive. It's called Mid-Level Vision Representations, Improved Generalization and Sample Efficiency of Visual Motor Policies, and an update that we published in Coral in November that's basically mid-level vision for navigation. And there was also another paper that had a very similar flavor concurrently came out that was actually published in, I don't remember actually, I believe in a robotics journal. And the title was actually, Does Computer Vision Matter for Action? Which is a very direct statement of the question. And the conclusion to both of these is that, yes, it's really important and critical to have vision pipelines. And the reason is, again, those priors. If you don't supply your robotic pipeline with these priors about the world, like the world is 3D, there are objects and there's permanence and so on and so forth, yes, there's a way that they can learn it, but it will take a tremendous amount of data, like millions and millions of interactions to recover those facts. So either we don't provide those priors and we directly use raw pixels, but the consequence of that is being inefficiency. As we know, let's say tabula rasa RL is very inefficient. That's why most of the time it's focused in simulators, because you cannot do as much interaction with the real world, or it will take years. Or we make ourselves prone to not generalization. You could solve the problem for a limited space for where you did learning. That's when the algorithms find a shortcut. But then the moment you go to a new building, because the same shortcuts that they used for learning, they was based on bias of data, so they wouldn't generalize. So both of these papers, and they strongly showed that supplying these priors, which is the job of computer vision, significantly improves efficiency, so it can learn faster with less data, and also it improves generalization. So what you learn in one building, it won't be specific to that one building anymore. So I think this was actually a very strong conclusion, and in a way response to demand for a study that it is really important for robotic pipelines to use like vision algorithms and priors. So I think that should basically summarize, or at least in my opinion, the important progress in vision for robotics in the past year.
The next area you had in mind was 3D vision, which we've actually talked quite a bit about in the robotics context.
Yes, exactly. So I think that the motivation is clear. The world is spatially 3D. But when we look at an image, we are looking at actually a 2D projection of it. So basically that calls for the problem of recovering the 3D structure. As a human, you understand the world in 3D. Just because the retina in our eyes receives a 2D projection, that doesn't mean we are unable to recover that underlying 3D. But we do that through multiple mechanisms, such as a stereo. We have eyes, so stereo is a solution to recovering 3D. But even when you cover one of your eyes, you can still see the world in 3D. Basically, it means some recognition or learning based is in process. So recovering this 3D structure from a 2D projection, such as an image, is a strong problem in vision community, especially in the past year. I think I see a rise. I think that was demonstrated by the fact that the paper award nominations in both CVPR and ICCV include actually papers in 3D. And also, I think the problem has actually another angle too in 3D vision. Now we have 3D sensors because 3D is important. We need processing pipelines for this 3D data. So this is different from the first problem that I mentioned. Image is 2D, you want to recover 3D, and then you'll do something with that recovered 3D. Sometimes we have the 3D from a sensor, like a LiDAR or Kinect and so on. But the processing pipeline that we use for images do not directly work on 3D data. They either work or they are very inefficient, or they just don't produce as much good results. So that's actually the second category in 3D vision, having pipelines for processing 3D data. Both of them, I believe, they expanded notably in 2019, and I see a rising trend over there. So I expect to see more and more of it in the years to come. I think they're like in the first, like, we can actually maybe talk about a specific example in each of these categories. Does that sound good to you?
Okay, yeah, absolutely.
Yeah. So I think in terms of like, generally when we talk about the first category of problems, recovering 3D from a 2D image, first question is that where we get the data. You have to have an image and have the underlying 3D data if you want to do it in a fully supervised learning manner to be able to learn, let's say, a neural network that receives an image and it spits out the 3D. So where we get the data. So 3D sensors are there, but they're less common than RGB. So we have a lot more RGB content than RGB plus 3D out there.
Mm-hmm.
A workaround that is common now is that people get RGB data, let's say a YouTube video or multi-view cameras, and then recover 3D using like classic methods like a structure for motion and SLAM and so on. And then once that is recovered using classic methods, they use the recovered 3D as a supervision for doing RGB to 3D from like individual frames, like monocular 3D.
Okay.
That has been working for a few years and has been shown like effective to a reasonable extent. One thing that makes that hard is dynamic content, because like those classic 3D reconstruction methods usually work based on point correspondences. And when you have moving objects in the scene, it becomes basically an ill-posed problem. Is it the 3D of the scene that is governing this motion, or is it actually there's like, let's say, a human that is moving in the scene and so on? So, and humans are actually specifically an important part because humans are a very important object in the world in general.
Right.
So there's one paper that I personally found like pretty cute in past year. It was learning the depth of moving people by watching frozen people. So it had a very interesting like workaround. There was the mannequin challenge that became popular. If you remember, it was about like people just standing stationary for a period of time, and somebody would film them. So that is actually interesting because they did a lot of data collection for us implicitly. So people just stood stationary and somebody walked between them. So we actually they collected a snapshot of the world where it was frozen and people were specifically there because it was mannequin challenge. So there was a moving camera, but no dynamic content. But whereas the rest of the times, it's really hard, if you think about it, to find people when they are stationary and then they don't move unless they are sleeping. When somebody is awake, there's usually some, at least micro motion. So mannequin challenge was great. That turned into a source of data that this paper used. So now they apply the methods that would not probably normally work for dynamic content and people, and the mannequin challenge data, and use that as supervision for now they can do depth of moving people whereas they actually learned it on frozen people. So they kind of tricked the system by learning from frozen people. But when you do it frame by frame, then it basically doesn't know that the person is moving. So that was an interesting paper, and I think it was a representation of the fact that still when we are doing 3D vision, data is a big problem there. And this paper actually addressed the data by this nice, interesting challenge that happened past year.
Yeah, it's a fairly it's quite creative, but it also
Exactly.
begs the question, for where will we get the data sets required to generalize this kind of approach, right?
Yeah, so like I said, there are aspects of the world that are static. Like I said, for instance, like in Gibson data, uh, these are human, like primarily these are like residential places, and people just go and scan them. And by default, there's little motion unless there's a human in the scene. So humans very often are one of the main sources of like motion, and there's some other forms of like motion too. Like if there's a fan on the ceiling that is like rotating, there's no human there, but
Mm-hmm.
there's motion there. So, but they're less common. So, and also like I said, humans are one of the most important objects in the world. So it makes sense to actually have processing pipelines that solve them, and then we'll take it from there. Yes, I guess we need to be either more creative, or we can hope for algorithms that come out and handle the dynamic contents better to be able to generalize it to the more general setting.
Yeah, and specific to this model is the idea that the model that's created with this technique could be kind of pulled out and used in a transfer learning kind of fashion in other pipelines, or that you would incorporate this process into other pipelines end to end, or none of the above. Is it just more of a proof of concept?
Well, I think the transfer, in a way that happened, was transfer from frozen people to moving people. So the data was purely from mannequin challenge, in which nobody's moving, right?
Mm-hmm.
By the definition of mannequin challenge. But once you learn from there, that doesn't mean that when you're using the learn model, it has to be applied on frozen people too. So think about it this way. Let's say if you learn a frame by frame processing pipeline out of the mannequin challenge, so it receives one image of a human, and it can recover the 3D. Now, during the actual data in the data set, the people are frozen. So five frames in a row, the person is frozen, so it's not moving. But it's a frame by frame process. Processing first frame is independent of the second frame and third frame. So at the test time, you can actually apply it on a video where people are moving, and it can just perfectly fine recover the 3D, because it basically bridges no connection between the first frame and second frame. So you can now apply that on moving people. And actually, they did show it in the paper that they learn on frozen people and they applied on moving people. And that's a consequence of the fact that, whenever you do, say, single frame processes, you can the frames are independent. That's actually an old trick. We have seen it before in many papers, and it goes from there. So so that's the type of transfer. I'm not aware of any sort of like other transfer learning being in play here. But if we have a pipeline that it can recover the 3D of people reliably well, I think that itself is a pretty important problem and worth attention. So that was an example from recovering 3D from 2D images. Like I said, the other batch of problems in 3D is processing the data that is 3D. Let's say an output of a LiDAR sensor or Kinect. Let's say to extract semantics out of it. You can do object detection given an image, or you can do object detection given a LiDAR scan. And you'd hope that if you have something like LiDAR, you would have more information than what an image gives you. So you should be able to do a better job. So there has been progress in general on this front in terms of efficiency and accuracy of extracting semantics given 3D data, whether it's LiDAR or Kinect and whatnot. There are multiple papers. Actually, there's I believe at Stanford there's a pipeline. It's called Minkowski engine that is focused on an efficient 3D processing. There's PointNet2 that came a couple of years ago, but it has been like matured since then. A few months ago in ICCV in Seoul, there was this paper on deep huff voting for 3D object detection in point cloud. That's actually another representative. I believe it was one of the award nominations too. So 3D sensors typically give you something like a point cloud, and then you want to do various type of semantic extractions on top of that. And object detection is probably the most nominal example. You want to put a bounding box around the objects that you see. So this paper actually had some pretty good results on that. And the idea in general was on voting. So when you look at, let's say, the point cloud is, as the name says, is a cloud of 3D points. And each point can vote for what kind of object that it belongs to. Like all the points that belong to a chair, that can vote for being a chair, and for like some parameterized like representative points, like say a center of the chair. And this paper actually used this voting pipeline and voting concept, and reported actually good results in terms of object detection. Something similar to that actually happened in 2D sector too. I believe it was called CenterNet and something similar to that, where like pixels in an image vote for the center of the object that they belong to. So that's, in a way, it's different from the preceding angle that was basically labeling each pixels on its own, like such as in segmentation and so on, or finding exact, like it wouldn't be a voting pipeline. That's the distinction between them. So I think that was also just to have a nominal example of papers that do 3D processing for extracting semantics, and I see that to be, again, a rising movement to develop more efficient pipelines within the vision community for recovering 3D or processing 3D, and doing more workarounds for lack of data there.
Let's move on to the next category.
Another area that I believe in 2019 continued to observe progress was self-supervised learning. In general, we can, I think, summarize that things are working sufficiently well for fixed mapping problems if you have enough data, meaning that if you have an image, you want to extract something out of it, let's say objects and so on. If you have enough data, it's a matter of probably designing your architecture and struggling with hyperparameters a little bit and training it for long enough, you'll get some sufficient results.
Mm-hmm.
The question that have been concerning a lot of vision researchers several years ago, after deep learning, probably immediately after deep learning wave came, was that what are we going to do if we don't have enough data? And that gave rise to multiple research directions, self-supervised learning being one of them. And I think the general question and the goal there is that you want to rely on less and less on human labeled data. You have a lot of data, raw data in hand, but just rely less and less on human labeled data and use raw data to identify trends in there, and then kickstart your learning pipeline to the point that the reliance on human labels is just only for the last mile and perhaps exceptions. So self-supervised learning has been going forward for a number of years. That you can actually look at the workshops within vision and machine learning community and you'll see that every year there's actually a popular workshop in that. In ICML last year, in 2019, we also had this workshop on self-supervised learning. Hopefully we'll have it again in ICML 2020. In CVPR 18, we had the beyond supervised. So there's a lot of basically focus on this problem in the community, and a lot of good researchers are focused on it. So it's not specific to 2019 as a trend, but in 2019, I think it was for the first time that we saw that the ImageNet problem essentially being solved with less labels. Or it was, to be more specific, it was the first time that without using labels, a self-supervised pipeline was able to achieve as good results that as a fully supervised pipeline would receive. And that was actually a good point. I believe there were like 2 or 3 papers that reported that success. The one that I particularly liked was there's a paper based on contrastive predicting coding. So this paper, the contrastive predicting coding, the title of the paper is Data Efficient Image Recognition with Contrastive Predictive Coding. So the contrastive predicting coding is not a new idea. It has existed before, but I think they really rendered it into a mature pipeline to the point that it's stable now, and it can, as far as this ImageNet dataset is concerned, you can actually get good ImageNet classification results without having to use the ImageNet labels, which is actually interesting and a good proxy for progress here. The contrastive predicting coding is one of the ideas that have worked towards this purpose. Is actually not a complex concept. In general, you can, let's say, you learn the regularities in the visual world to be able to learn good features out of it. Let's say if I show you the top half of an image, you'll have an idea of what the bottom half would be. Like if in the top half, if you see like a head of a dog, probably you would say in the bottom half there would be the body of a dog. Mm-hmm. So now, when would you be able to make that prediction? You would be able to make that prediction when you know how the world looks like. You know that dogs are not just these like heads that are like floating in the air.
Right.
There's usually a body to support it. So the raw image, if you have a lot of them, is enough for learning that. So that's basically like in a very simplified way, the idea behind like predictive coding. You show part of a data and you learn your system to predict the rest of the data. And this requires no labeling because the data is like raw and available to you. You just mask it during learning and you get the neural network to predict the masked part. So that this turns out to be actually a good way of learning features. Mm-hmm. And the paper that I mentioned actually uses this idea in a more advanced way to not rely on human-defined labels. That's in contrast to, let's say, something like AlexNet that basically just started from images from the iteration 0 of learning. It would map pixels into human-defined labels. Human-defined labels, of course, there was 1,000 classes, but actually, like every single instance of an image was labeled by an annotator. So that was actually there. I think that what we need to be aware of for the year to come is that this was shown for ImageNet. And this does not mean that we can do this for all problems in Vision and under all settings. So the caveat essentially is that this is a specific setup. There's a certain architecture, there's a linear layer and so on. This doesn't mean that this will continue to happen regardless of these design choices. And but still, we didn't have this even this prior to this year. So I think there's something to celebrate here. And the more importantly, even if it was architecture agnostic, this is about ImageNet. And ImageNet is not the world. It's a very niche part of the world. It's a very dog biased part of the world because there are like many dog classes in there. And then, for instance, from other species and animals, there's like less of them. Mm-hmm. So, of course, this is about the bias that the design of any data set involves. The fact that we showed this on as a community on ImageNet, that doesn't mean that we can show it for everything. So we can call it a success when for any image recognition problem, we would have a self-supervised learning pipeline in which we would not have to rely on human labels too much and be able to solve that problem. Let's say if somebody does that for depth estimation or object segmentation and so on, then it would be a lot more convincing. But that was definitely a progress for 2019 in self-supervised learning too.
Now, we've seen 2019 and 2018 as well has brought self-supervised learning to the fore on the NLP, within the realm of NLP in a big way with models like BERT and Elmo and others. Is there a relationship between the this being a focus area at Vision in the vision space, do you think that we're kind of pulling from, inspiration from, one to the other?
No, it's actually a great point. It's both ways. Like predictive coding, in a way, actually has similarities to the models that work well in NLP too. So, like a language model in general is something similar to that. Like you give the beginning of a sentence, whether as character or words, but you give it the beginning and you train the system to predict what comes next. And it can push it really, say, not just the next word that comes, but many words that come after that. Or you can turn it into like fill in the blank problem. So it's all about like masking part of the data and filling it in, whether it's the next part of the data or some like preceding part of data. But the common gist here is that we use raw data to be able to we define a problem that is primarily based on masking part of the data and get the system to learn to fill that gap. And that is just a good feature. And then what comes out of this like pipeline is a feature. Whether it's learned on text, yeah, it becomes something like BERT. If it's learned in images, it becomes something like the predictive coding pipeline that I mentioned earlier.
Mm-hmm.
And they become good features that are just sufficiently, at least as far as, let's say, for images, image that was involved, sufficiently universal. So you could use those features to read different things out of it, such as like ImageNet classification. So yeah, there are similarities actually, and I see that going both ways. There are many people that work on both the self-supervised like models for both image and text. Another category I think is worth mentioning, and it's interesting to me, the connection between adversarial robustness research and vision. So it's basically an interesting finding. So in general, the robustness issue is that you would have an image recognition pipeline, let's say object detection, and turns out that if you can make very small changes in the input, something that humans even won't see, like adding a few pixels or making a change, like very tiny changes in the pixels, there's a way to actually mess with the object detection pipeline, whereas the humans wouldn't see that change at all. So that kind of made it raised a big question and made a lot of people concerned. Also, it's besides like the concerns on safety and so on. It was actually an interesting question intellectually, that why is it that image recognition pipeline that seemed to be working well, there's such a big loophole that we can mess with the pixels in a very imperceptible way, that changes the output such drastically. So there has been progress in the community of adversarial robustness community, towards like methods that just robustifies the neural networks with respect to these changes. A lot of work came out of Alexander Madry's group at MIT, and they showed actually good progress towards like high frequency adversarial patterns, and they basically augment the training of a system in a way that the outcome is invariant in respect to that kind of noises, and then therefore you would expect more robustness. And indeed, the system does become more robust, at least with respect to that particular adversarial pattern.
Mm-hmm.
Now, I think what was interesting, in retrospect, it's common sense, but it had to be shown that if you robustify a image recognition pipeline, you would expect it to have a better understanding of the world, and therefore it should actually work even better for applications that are not within the context of adversarial robustness. So let's say if you have an image recognition pipeline that with a little bit of changes in the pixels around the dog, it would just misclassify a dog for an ostrich.
Mm-hmm.
And it just basically means it didn't quite understand what a dog is. So it was prone to these kind of mistakes. Now, if you have a robust system that it doesn't make that system anymore, it means it better understood what a dog is. So it better understood the manifold of real world images and what's possible in the real world and not. So there was this paper actually in NIRBS just 2 weeks ago, from Alexander Madry's group, that basically showed that if you have a robust image classifier that is like trained with this robustness mechanism, you can use it to synthesize better looking images compared to the same exact classifier just without being trained with adversarial robustness. The title of the paper, I believe, was Image Synthesis with a Single Robust Classifier. And they basically showed that side by side, if you look at a synthesized image coming out of a neural network, in image synthesis pipeline, we always use some sort of pre-trained neural network, an image network and whatnot. That's a requirement in the system. So for that pre-trained neural network, if you use a robust classifier versus a non same exact data, same exact architecture, the robust classifier just renders much better looking images for various kind of synthesis problems like in painting or transferring sketches to images or super resolution and so on. So this was an interesting finding. It, like I said, it makes sense because, of course, a more robust system, you would hope that it understood the manifold of real world images better. So therefore, it should be able to do better synthesis too. But we finally have a paper that actually showed that too, which I personally find interesting. And it's another example of the mix of different areas between vision and this time adversarial robustness research.
Mm-hmm. The generalization result makes me think a little bit of the parallel to multitask learning, where we've seen over the past, relatively recently, I think past year or two, a lot of work's been going into multitask learning that showed that just the addition of another task in the training process helps the networks generalize and perform better. In a sense, often in this, in the adversarial robustness research, the robustification of the network is another task. And so these are kind of similar results or related potentially results.
Right. To some extent, that's true. Like essentially, the robustness is as a result of augmenting the loss with additional terms that you wouldn't normally have. And you can view as multitask learning versus single task learning as augmenting the loss of a single task framework with more losses, like more tasks that they wouldn't normally have. So there's that like regularization effect that though I have to say that in multitask learning, that observation has been challenged in quite a few different settings. It really depends, for instance, what tasks that you learn together to be able to actually see the benefits of multitask learning. Ironically, actually, we published one paper on this area, which is exactly called "Which Tasks Should Be Learned Together in Multitask Learning," and that the title says it all. That there's a question there to ask. Like, it's just being multitask is not necessarily better. There's like multiple other parameters in play, such as what tasks should be learned together. And there's also like an equal amount of research going into, let's say, even if you know what tasks that you want to learn together, what the architecture should be, how the sharing exactly should happen. Should it be like soft parameter sharing, hard parameter sharing, some sort of progressive sharing where you decide what parts of the parameters and layers should be shared and which parts should be dedicated to networks, to different tasks. So to be able to get the benefits of multitask learning, I personally believe that a lot more research has to be done. And the examples that we see are probably when we got lucky and they worked out. It doesn't mean we completely understood the problem yet.
So, there you have it. We've kind of gone through these 4 key areas that you see us making some advances in the vision field in 2019. And those are primarily from kind of the academic perspective. How are you seeing these trends play out in the real world?
Yeah, I mean, I think if by the real world you mean like who has used them or in terms of like commercials, I think probably I see 2 areas. Image synthesis, like I said, it entered the new maturity level. Like we see apps that come out that actually use these kind of learning-based synthesis that was, I think, a child of the marriage between vision community and graphics community. And these apps that like transfer you from like young to old or like smiley to not smiling and so on and so forth. And then there's companies like NVIDIA. I know that they're active in that, and it had the consequences of the photo fakery concerns like deep fakes and so on. That if things become so well, then how do you know when something is real and when it is not? But it's safe to say that that technology has been proven effective and has been adopted. So that's one area
Mm-hmm.
that I see. It entered a maturity level that was commercialized and also used by ordinary people on their phones and so on. Another interesting area continues to be autonomous driving. Um, Again, an autonomous car is actually a robot. It's a big robot. It has sensors, it has perception, it has planning, it has control, though it's a specific one. It's one for navigation, designed to move on the roads that marked up, and so on and so forth. So in a way, it's an example of like robotics, vision plus robotics. And again, commenting on the perception aspect because there's a lot of things that go into getting something like autonomous driving car to work. Um,
Sure.
we saw progress. Tesla continues to release new features like a smart summon that you can call the car to come to you in a parking lot. And the Waymo, I heard during NeurIPS that they just released an app that works in Arizona. Then you can actually order cabs that are completely autonomous. There's no person in the cab, from what I know. I haven't used it. I haven't been to Arizona since I heard this, but I'm looking forward to doing it.
Mm-hmm.
So Waymo did that, and it's I actually find it impressive. We'll see how it plays out, but you can actually have these autonomous cabs now. And different companies have different approaches. Like, we know that Tesla is, Elon Musk, and he has been vocal against like using heavy 3D sensors like LiDAR. Waymo has the safety first approach, even at the expense of like having more sensors on it. So different companies have different approaches. And like I said, we have seen progress, such as the Waymo release or Tesla features. But one summary I have is that, again, the last mile has been proven to be more difficult than the optimistic anticipations like a few years ago. And many people had like predicted this, like Rod Brooks and so on. If you look at the predictions about like when autonomous driving would be here, let's say 5 years ago or 3 years ago, let's say we would hear by 2020 it would be available, but it wasn't. Then 2000, say 18 and 19, they would push it like
Mm-hmm.
a little bit more into the future, like 5 years. And in 2019, we heard this question multiple times answered by we don't know exactly when it'll be here, which is representation of the fact that again the last mile has been like proven to be harder than the optimistic anticipations. But I'm watching it actually carefully because it's an interesting area. There's a lot of investment in it. There's a lot of talent going in it. So
Mm-hmm.
if something wants to work, I believe autonomous driving will be one of the first examples of as the application of say vision plus AI, machine learning, and so on. And so we'll see how it goes.
Do you think the last mile problem applies specifically or only to autonomous driving, or do we see this generally across bringing research-based innovations in the vision domain into real-world
No, I
application?
absolutely see it as the latter. It's not about autonomous driving anymore. Any real world system has a lot of unanticipated issues that you probably won't even think of before you reach there. And many of these pipelines that we have right now, they have caveats. Let's say if you have a sensor that it works fine, it might continue to work fine during summer, but during winter when it snows, how do you know how it's going to react? Or like let's say something like
Mm-hmm.
autonomous driving, or even like say indoors navigation. If you have a robot at home that like navigates safely from one point to another, let's say when that happens for household robotics, I'm pretty sure that you'd be surprised by the way the system works when you take it to a different country, when the houses look different, or things that are okay here, they're not okay there, and so on and so forth. So no, I definitely believe that any kind of real world like adoption of this research that we are doing, especially in terms of machine learning, where there's a factor of uninterpretability as of now, the last mile will be proven harder.
So let's shift gears from looking backwards into 2019 to looking forwards to the future. Maybe give us your top predictions for computer vision for 2020 or beyond. I've been challenging the folks that I've been doing our AI Rewind series this year, since we're at the end of a decade, to project a decade to the future. No one takes me up on
I
that.
want to. The problem with making predictions is that there's a pretty good chance that for turning out to be wrong. Like if a decade ago you
Of
asked
course.
anybody about deep learning, I'm pretty sure the chance of that being the prediction would be, even though it just, like it's in 2010, it just happened 2 years after that in computer vision. But
Yeah.
I'm not sure if anybody saw that coming, but maybe some people say they saw it coming, but they were probably a very, very small percentage. But I think, I can extrapolate a little bit, at least if I don't even make, too controversial like predictions. One thing that in terms of, since we just finished the commercial discussion, I think at least I can say that from the commercial development perspective, I'll continue to watch autonomous driving progress. I really view that as a good proxy for progress in a well-focused and well-invested area. So lack of talent, lack of data, lack of money is not really an excuse. So we are really down to solving the problem, the physical problem over there. And one of the other reasons that I particularly watch autonomous driving progress is that perception-wise, ironically, autonomous driving to some extent is a simplified case compared to the general perception case. There are complications, but the reason it's simplified compared to general perception is that, like, in autonomous driving, there are like lane markers and there's signs and there's some code of conduct and there's a lot of data. So the lane markers are, designed to tell you where you are. Whereas, like, when you're just walking in the woods, there's no lane marker. So it's the same navigation problem, but it's the loss, kind of a lot less information. There's a lot less sort of design ahead of time that's gone into making the problem perceptually simpler. So if we can solve, let's say, a lane detector for autonomous driving, a big problem is solved. Like for a general, say, navigation problem in a structured setting, there's no lane to detect. So you have to really do something more than that. So in some senses, autonomous driving's perception is simplified. So I'm hoping to first see the simplified problem solved before we even like dream of solving the more complex and unstructured problems. But of course, there's like other big issues over there. Like there's safety risk. The speed of autonomous driving is high. That basically means you have very limited amount of time for making decisions. You have to make decisions like way ahead of time compared to the normal setting when the speed is like low and then sensitivity is high, because there's like a risk of fatal accidents and varying conditions. Cars go everywhere, in like during the night, during the day, during the snow, foggy, and so on and so forth. And sensors get constantly interfered by sun and whatnot, and you're capped by the price. So there is like, that's not to basically play down to complications, but at least, let's say, purely focusing on the detection aspect, there are some things in autonomous driving that are simplified. So I continue as a vision researcher to watch autonomous driving progress and to see where that goes and when it is that we are going to finally seal it and say that we safely have autonomous driving system. And so that's a good proxy for me that I watch. Another aspect that I think it's outside this niche, or like more specific applications like autonomous driving. If we like there are like other applications that we could watch. There's actually a lot of focus on like a startups on robotics that, of course, they need to solve vision too. Some of them are focused on warehouses, some of them are focused on indoor spaces. But if you want to think about like more like general settings about vision, commercially speaking, I look forward to more like democratization of vision pipelines. So there are APIs right now So it's a very democratic way of using vision. Like if you're somebody that has no expertise in vision, you can actually use Microsoft Azure or Google Cloud to do certain tasks like face detection or some object detection. But compared to general, what vision can do, that's a very small part of the potential. So another good proxy for progress is that how much these democratic tools of vision, how far they go, how much we go beyond like face detection and so on. And like I said, there's a good reason that these APIs have these now, because they are the things that work good. Then many other things that we have, they just don't work good enough to be at the API level. And that's why I'm saying like the more I see brought to the API level that works reliably and sufficiently well, that's a good progress proxy for our progress that we can see. And examples are like 3D again. There's no good API, at least from what I know, that would recover the underlying 3D structure from given images for you. There's like
Are you
networks that.
predicting that for 2020?
Well, maybe. Let's like optimistically. Yeah, I don't know whether we are going to get to the API level. Probably not, but I think the progress in the field points to the direction that people will start like thinking about bringing that to the API level. Hopefully, based on the progress they'll make in 2020. So yeah, I'm also observing these and looking forward to more like democratization of the tools that we have in vision, because that's really when, as vision researchers, we will let the product of our work to be used by people that are not vision researchers.
Yeah.
So that's,
Awesome.
I think, from the commercial perspective. From the technical perspective, I think actually the trends that I anticipate would be more or less an extrapolations of the trends that we discussed. I do believe that Vision plus robotics will continue to go forward strong. The way it will change is that we will actually start working on more specific, more general problems. Like right now, let's say in this example of like habitat challenge and Gibson to discuss, things were primarily about navigation. And even within navigation, it was about one case of navigation, like go to this particular coordinate. But looking at the more general setting of find objects for me or solve the tasks that, or like a sequential game, like find object A and then go to an exit. Like an example, let's say is the rescue robot. You send a robot to a building that is on fire. This robot has not been in this particular building before, but you task it with find the victim and go to the closest fire exit. So it's a really useful application, just that, but we are not there yet. So in terms of Vision plus robotics, I expect the proportion of researchers interested in this topic to expand, and the technical part, the problems to become more challenging, more realistic, and hopefully work under more general setting, not limited settings that we have been focusing on so far. I multitask learning came up in our discussions, and I think that's an area that I hope to see progress in it. Generally, there's very little things about vision that is single task. Like your job with an image doesn't end the moment you detect objects in it, or the moment you detect the depth of it, the moment you detect the vanishing points. For any practical use, for most practical uses, you usually need multiple of things of such task at the same time. So the problem is like essentially multitask to be useful. So being able to bring multitask learning to a more reasonable state where we can solve multiple problems efficiently and reliably and consistently is an important problem. We did see some progress in 2019, but we are far from reaching that level to the point that we can supply a multitask vision pipeline with one image. And in the output, it produces a breadth of different abstractions extracted in a way that is done independently, that is done efficiently. Of course, you can have like under the hood, you can have like n different independent pipelines for n different tasks. That's inefficient because there's a lot of redundancy between them. So you don't want to do that. Being able to do that efficiently, do not sacrifice the accuracy over there. All these n outputs should have a reasonable quality. And something that I'm personally excited about these days, and hopefully soon we'll release the stuff on it, is on consistency. So the output of a multitask system should be consistent. Your objects and your 3D cannot be inconsistent with each other. So how we actually do the learning in a way that the outcome has some guarantees for being consistent. And one thing that also I think we have overlooked for too long, especially again in the context of multitask learning, is uncertainty. For each of these outputs, sure, we are providing some predictions, but you can't do much with a prediction, especially as a practitioner, if it's not associated with some confidence metric. This is a dog in an image, but with what confidence? If you're 99% confident and versus you're 50% confident, your decision probably changes. If there's a tiger within like 2 meters of you with 99% confidence, I'm gonna run. If it's 1% confidence, probably I'm not gonna run. I'm gonna do something else. So there's a real value in extracting uncertainty from the visual signal. Surprisingly, that's not actually a big part of the computer vision research right now, and I think that's part of the reason that's happening is that the Vision plus X movement is recent. So the moment you want to provide vision outcome towards some downstream goal, whether that's a roboticist or some and so on and so forth, you realize that they need a little bit more than what we are providing them. And one of the things that they definitely need is uncertainty estimation.
And so you bring this up in the context of multitask. Is the idea that the consistency desire and the uncertainty desire can be formulated as additional tasks or objectives as part of your training?
Right. The reason I brought it up in the context of multitask learning is that multitask learning itself provides an opportunity for a new way of quantifying uncertainty. But uncertainty is still useful, and it can be done in a single task setting too. And in the machine learning community, there's actually work on it, more than vision community. That systems that supply a confidence score besides the prediction that they're making, even that's a single task. There's like research being done on that and so on, but it has been, again, proven harder than anticipated because neural networks were found to be making confident mistakes. So because of various different things, that's most of them are actually theory. There are papers in just past ICML. There was probably more like a track that why this is happening. That's basically a question rather than something that we already know the answer to it. But we have made this observation that neural networks make confident mistakes. So that's a problem. So basically means that even if you have a measure of uncertainty, chances are that might not be reliable very if you extract that uncertainty out of a single task system, there's no redundancy over there or there's no ensembling, that uncertainty estimation might not be very accurate too. So in multitask setting, there's a way to solve that because essentially under the hood, there are multiple processing pipelines for different abstractions, and the consistency across them is actually a good proxy for how accurate each of them are. And there has been research on it, and hopefully, I think soon, maybe within a few weeks, we will also release new material on that. But from what I see, the meta point is that we definitely need to output uncertainty estimates out of the visual processing pipelines that we do, and more specifically on multitask learning and so on. What I see is that there's a good opportunity to solve that problem, at least within the multitask learning framework. And we'll see how 2020 turns out.
Awesome. Any additional predictions for us?
I think that's it. That's enough to embarrass myself in a year from now. So
you heard it here first. Autonomous driving in 2020. That's what you said, right?
Well, I didn't, for the record, but I hope.
Nice. At the very least, Amir in an autonomous vehicle cab in Arizona.
Yes, that's at least a thing there, and I'm looking forward to trying it.
Awesome. Well, Amir, thanks so much for taking the time to share with us your take on 2019 and predictions or anticipations for the year ahead.
Thanks for having me.
All right, everyone, that's our show for today. For more information on today's guest or for links to any of the materials mentioned, check out twimlai.com/rewind19. Be sure to leave us a 5-star rating and a glowing review after you hit that subscribe button on your favorite podcast catcher. Thanks so much for listening, and catch you next time.